Mutual exclusion means that at any moment, only one process can use a particular resource. Imagine a single-person bathroom. While one child is inside, nobody else can enter. In a computer, a printer, a disk, or a piece of memory can be used by only one program at a time. If the resource cannot be shared, the system must enforce a lock so that others wait until the current holder finishes. This is the first ingredient that can lead to deadlock, because some processes may be forced to pause forever if the lock is never released. Hold and wait describes a situation where a process is already holding at least one resource, and while still holding it asks for another resource that is currently held by someone else. Picture a child holding a red crayon called Resource A, while asking for a blue crayon called Resource B that belongs to a friend. The child does not put down the red crayon while waiting for the blue one. In operating systems, this behavior creates a chain of dependencies that can become a loop, setting the stage for deadlock. No preemption means that once a process gets a resource, the system cannot forcefully take it away. The process must release it voluntarily. Think of borrowing a library book. The library cannot yank the book from your hands. While you are reading it, you must return it yourself. If a process refuses to give up a resource, perhaps because it is stuck, the system cannot intervene, and the deadlock may persist. Circular wait occurs when a group of processes form a closed chain, where each process is waiting for a resource that the next process in the chain holds. Imagine 5 children sitting in a circle, each holding a different toy, and asking the neighbor for the toy they want. Because everyone is waiting for someone else, no one can move forward. In a computer, this cyclic waiting is the final piece that turns the previous 3 conditions into a deadlock. A resource allocation graph is a visual way to show which processes hold which resources and which processes are waiting for which resources. The graph has 2 kinds of nodes: circles for processes P1, P2, and so on, and squares for resources R1, R2, and so on. An edge from a process to a resource P to R means the process is waiting for that resource. An edge from a resource to a process R to P means the resource is currently assigned to that process. If you can walk around the graph and return to the starting node following directed edges, you have found a cycle, which indicates a possible deadlock. Algebraically, the 4 conditions can be expressed with logical formulas. Let capital M be the set of all resources, capital P the set of all processes, and H of open parenthesis P, R close parenthesis, a predicate meaning process P holds resource R. The conditions are: mutual exclusion. For all R in M, there exists exactly one P in P such that H of open parenthesis P, R close parenthesis. At most, one process can hold a resource at a time. Hold and wait. There exists a P in P such that open parenthesis there exists R sub 1 in M such that H of open parenthesis P, R sub 1 close parenthesis, and open parenthesis there exists R sub 2 in M such that not H of open parenthesis P, R sub 2 close parenthesis, and request of open parenthesis P, R sub 2 close parenthesis. No preemption. For all P in P, for all R in M such that H of open parenthesis P, R close parenthesis, implies not preemptible of open parenthesis R close parenthesis. Circular wait. There exists a set of P sub 1 through P sub k that is a subset of P such that for all I, 1 less than or equal to I less than or equal to k, there exists R sub I in M such that H of open parenthesis P sub I, R sub I close parenthesis, and request of open parenthesis P sub I plus 1, R sub I close parenthesis, with P sub k plus 1 equals P sub 1. All 4 must be true at the same time for a deadlock to exist. These formulas let us reason formally about the problem, and also guide the design of detection algorithms. Practical illustrations. Dining philosophers. 5 philosophers sit at a round table with a fork between each pair. Each philosopher needs 2 forks to eat. If every philosopher picks up the fork on their left and then waits for the fork on their right, we have mutual exclusion. Only one can hold a fork. Hold and wait, holding one fork while waiting for another. No preemption, forks are not taken away. And a circular wait, philosopher 1 waits for philosopher 2, philosopher 5 waits for philosopher 1. The system deadlocks, nobody can eat. Printer spooler, process A holds a file handle resource 1 and requests the printer resource 2. Process B holds the printer and requests the same file handle. Both processes satisfy the four conditions, leading to a deadlock where the print job never finishes. These everyday-like scenarios help children see how waiting for each other can freeze the whole group. To prevent deadlock, we can break any one of the four conditions. A common design is to break hold and wait by forcing a process to request all the resources it will ever need at once. In a classroom, this is like a child asking the teacher for both the red and blue crayons before starting a drawing. If the teacher cannot give both, the child simply waits without holding any crayons. In operating systems, the protocol works like this. 1. When a process needs multiple resources, it first releases any it currently holds. 2. It then requests the full set together. 3. If the request is granted, it proceeds. Otherwise, it stays idle and tries again later. By never allowing a process to hold one resource while waiting for another, the circular wait chain cannot form and deadlocks are avoided. Detection algorithms periodically examine the resource allocation graph for cycles. The classic wait for graph simplifies the resource allocation graph by connecting only processes. An edge PI arrow PJ means PI is waiting for a resource held by PJ. Visited equals empty set, stack equals empty set, function DFS of P, add P to visited, add P to stack, for each neighbor Q of P. If Q not in visited, then if DFS of Q returns true, return true. Else if Q in stack, then return true, cycle found, remove P from stack, return false. If a cycle is found, the system knows a deadlock exists. Recovery strategies include process termination. Kill one or more processes in the cycle, choose the one with the smallest cost, for example, lowest priority or least work done. Resource preemption. Force a process to release some resources, possible only for preemptible resources like CPU time. The system may need to roll back the process to a safe state. Rollback. Restart the affected processes from a checkpoint after releasing their resources. These techniques let the system break the deadlock, much like a teacher stepping in to separate the children and give each the needed crayons so they can continue playing.